Yeah, so the next speaker is Thomas Lamiaux, who's doing an internship at the Technical University of Delft, and he'll tell us about computing cohomology rings in Cubical Agda. Good luck.
So I'm going to talk about some work that we've done with Axel and Anders that was recently published at CPP, which is about computing cohomology rings in Cubical Agda, and the hard part is actually to formalize it. So the first thing is what is cohomology, and let's start with cohomology groups. Well, a basic question that we can have is how can we tell two topological spaces apart? And if, for instance, you look at the Mickey Mouse space and the plane bottle, you can kind of see intuitively that they're not isomorphic, and still you will have a hard time finding a precise mathematical reason why. And that's why cohomology groups were invented. The point is that given a topological space X, we associate a sequence of abelian groups, named the cohomology groups, that are invariant. It means that if you have a cohomology group in the sequence, which is different from two spaces, then they won't be isomorphic. And the point is that they're supposed to be nicer than homotopy. They're supposed to be relatively easy to compute and nice enough to be able to compare them easily. And indeed, you can compare a lot of spaces this way. For instance, the plane bottle is different from S1 by H2. Same for the real projective plane, or the complex one, and from the Mickey Mouse space. So you can really use it quite quickly in art to distinguish a lot of spaces. Moreover, we're working in art, so everything is nicer in this case. Indeed, cohomology has a very short definition. It's just the function into the I sphere that you truncate because you don't want extra information. And you get all of the benefits of working syntactically. Everything is defined by induction, from your spaces to your function and so on. Oh. So basically, in my opinion, you have a shorter and graspable definition of cohomology because it's really easy to understand how truncation works and stuff like that. Moreover, you can use it by induction when you're defining functions. So you can basically split the complexity into different cases. And also you're synthetic, so you have no points. Makes a lot of definition much nicer. Also, you get a simple and short computation for many cohomology groups, and functions are supposed to compute. So, what is the point of cohomology rings if we can do so much stuff with cohomology groups? Well, there is some spaces that have the same cohomology groups, but are still different. And this is because cohomology groups are just invariants. Thankfully, cohomology groups, when you consider them all together, have more structure. They have a graded operation from hi to hj to h of I plus j that is graded and enables to turn the direct sum of all the cohomology groups into a ring, which is named the cohomology ring. And the point is that this ring is one more invariant. If two spaces have different cohomology rings, the cohomology rings are not isomorphic as a ring, then the topological spaces are not isomorphic. And for instance, for CP2 and S4 wedge S2, even though they have the same cohomology groups, they have different cohomology rings. So what is our objective here? Basically is to characterize the cohomology rings of different spaces, for instance, the plane bottle, as the quotient of a multivariate polynomial ring by a finitely generated ideal. So the challenges are first, we need to define a direct sum, which is practical enough to define graded rings, which is just a nice abstraction for cohomology ring, or it's just groups and a graded operation. You also need to find a practical definition of multivariate polynomials, because, for instance, a definition based on list may not be very practical to use, and you need to define function in and out. And lastly, you need to prove that this is a ring isomorphism. So you need to prove that the product is respected. So you need a definition that has a product which is nice enough to handle. Moreover, we have two constraints. We're in Agda, so we don't have tactics. So we can't brute force bureaucratic details using tactics. So we need nice definitions. And we want to stay constructive to preserve computation. So if you want to build a direct sum, well, we could first start at looking at what people are doing in classical mathematics. So basically, they say it's the sequences that are null outside of a finite interval, finite subset. And you could try to translate this directly to art, but you have an issue is that you need a notion of finite subset, and this does not behave correctly in art unless I has decidable equality or something like this. Well, in our case, we want the index to be n, so we could restrict that because on n, finite subsets are included into initial segment, and you could just say, oh, those are the sequences, the function that cancel after a point. So let's do that. Then you can try to define a group structure. It's sequences, you can just add them pointwise and it will work. But the real issue arises when you start trying to define the product. Indeed, you would like to say that given a graded operation, the product is just the sum, yeah, it's not sigma the sum, of all the pairs fi star g of n minus I, because this way you end up in g of I plus n minus I, which should be g of n. The issue is that in HoTT, this will only hold up to a path and not definitionally. So basically, all of those objects belong to different types. So you're forced to add transports everywhere to make stuff work. And basically, if you try to work with that, you're gonna go down into transport L. So if you want to prove associativity, looks kind of like this. The usual formula with transports now. So you have to change transport, you have to like change index in the transport, everything is awful. So could we do something a bit better? Well, we could do something which is a bit more type-oriented, and we could use the fact that we have induction and quotient in Cubical Agda. So you can give this really big definition that looks a bit scary, but basically it's just saying that the direct sum is the colimit in the category of abelian groups. So basically you have a 0, a plus, and the lows of the abelian group, so just the free structure. And you have a base constructor, which is the injunction. And you can think as base of n and the coefficient as just the sequence, which has zeros everywhere except in n, where the coefficient is a. So you find the usual definition, but here you have to add set truncations because we're doing algebra and everything is supposed to be a set, and this couldn't be otherwise. What is really nice about this definition is that now you can work with recursion. And indeed, if you want to build a product, you can just do a double recursion on both arguments. When you're in the base case, you just consider two elements separately. So you can just say it's the base of n plus m and x star y. And because you're no longer considering a sequence of terms, so all of the terms together, but two terms separately, you don't need transports anymore because you're trying to sum them. So it's really nice. And in all of the other cases, it's going to be completely trivial to define now. Because basically, if you have a 0, it cancels on multiplication. If it's a plus, it distributes. And if it's any other equation that you must verify in the quotient, it's going to be trivial, like in a line. And if you want to prove associativity, it's exactly the same. Triple induction. You get the base case, which is basically just associativity but dependent, because you're in type theory. And this is actually an axiom of a graded operation. So it's true by default. And all the rest is trivial. So with this definition, you can actually formalize graded rings and cohomology rings very quickly. Like, I don't know, in 200 lines. And basically it's just long because we have 8 cases to do each time, but there's no difficulty anymore. But we can go even further. We can actually use a direct sum to define polynomials. We can say that the polynomials over R is the graded ring for the constant group, which is the underlying group of the ring, and the graded operation, because there's no more, all the groups are the same, it's just the product of the ring. And we can do even better. We can define this way, multivariate polynomial ring this way. We can just say it's a constant ring over the index n power n, which gives us n variables. And this is really crucial for our purpose, because now the polynomials and the cohomology ring are defined in the same way. So when you formalize, you won't have to change data structures. You won't have to switch from like a list to anything else that would be tens of lines of code. Now everything is going to be really straightforward. Moreover, furthermore, you have a very direct definition of multivariate polynomial ring. It's not defined by iteration, as you may find in a lot of textbooks. And the best thing about that is that it's actually intuitive. Basically, the elements are 0, ax power n, which is basically the base constructor that we had before, n plus, and the product is just generated by the usual equation for polynomials. So this is basically really nice because it answers all of the questions that we had before and that we were requiring to be able to compute and prove ring isomorphism for the cohomology ring. And we can go even further. We don't actually need to give up on the function definition the sequence definition, because we're in homotopy type ring, we can decompose our rings in a row ring structure, which is basically the operation of a ring, and is ring, which is just verifying that the operations verify associativity and all of the properties of a ring. And because we have defined a row ring for the id definition and for the fun definition, we just need to prove that they are equal to transport the ring properties from the id definition to the fun definition. And to do that, we have the structural identity principle that just says that when two rings are equal, when they are isomorphic. And so basically, all we need to prove is that the two row rings are isomorphic as row rings, which is basically isomorphic as rings. And then we can get all the proof for the fun definition for free. And what is really nice is that you would have to do it anyway, because if you had defined the two definition of graded rings separately with two different definitions, you would still have to provide an isomorphism to show that they are actually the same definition. So you may as well do this directly and transport the proofs once you've done it once. So now let's look a bit about how can we prove the isomorphism. Well, we want to prove isomorphism of the sort. Basically, the cohomology ring is isomorphic as a ring to multivariate polynomials quotiented by affinity generated ideals. So we have decided to use a method which is just based on building the functions in and out. We're not working with kernels or stuff like this because it was actually very direct, slightly long because there's a lot of cases each time, but straightforward. So basically, we start by building a function, C, from the multivariate polynomial ring, not yet quotiented, to the cohomology ring. Then we prove that C is a ring morphism. And the point of doing this at this level is that we just need to prove that C cancels on the different elements in the finity generated ideal to get a ring morphism on the quotient. This way we can handle quite nicely the ring morphism part, which is hard to get directly on the quotient. And then we can just define directly an inverse and prove it's an inverse left and right. So how does it work here? Well, what is really nice is because of data structure, now you have the same definition for the cohomology ring and the multivariate polynomials. So basically, you're going to have 0 on 0, plus on plus, and you will just have to handle the base case, which is what you want to look at. Moreover, if you want to prove that C is a ring morphism, it involves to proving that C respects the product. So basically, that the product of your ring that you're trying to prove it's isomorphic to is preserved compared to the top product. So basically, characterizing the cohomology ring of a space now just unfolds to characterizing the cup product. So it means that you have managed to get away from all the bureaucratic details to only focus on what you care about. Moreover, by the definition of the structure, C is just going to cancel by definition on the finity generated on the element in the finity generated ideal. So thanks to the structure, you can only focus on the cup product. So now that we have said that, how can we actually do this? Well, basically, those are equations. You would think, oh, maybe you can actually compute them. After all, we are using synthetic mathematics. That's kind of the end goal, to be able to compute stuff. Well, for the Klein bottle, it's going to just unfold to prove that if you name phi1 the computation of h1, it's just proving that phi1 squared is 0. So if you try to compute that, well, it doesn't exactly work. If you try to compute just phi1 of 1, I have to stop it after 10 minutes of computation, 3 gigabytes of RAM. So it doesn't exactly work. And the worst thing is that you actually try to compute the cup product, so the square of that. So it's going to be even worse. So there is a trick. The trick is to define an alternative generator, alpha. And then you prove using computation that phi1 minus 1 of alpha is 1. And just you run it. And the point is that alpha is going to be really nice. Like here it's 4 lines. Normalize it's at 8 lines. So you can get that by computation. And then just conclude for free that alpha is equal to phi1 of 1. And so then you can just try to prove that the alpha cup alpha is 0, which can be done on 10 lines. So basically, you're bringing yourself to working with a nicer generator rather than working directly with phi 1 of 1. Otherwise, you would have to look at what is the definition of phi 1 to prove that it is actually equal to alpha, whereas you can do it for by computation. So if someone gets into this philosophy, he would say, why don't we compute alpha square, alpha kappa alpha? Well, it's a good try, but doesn't work either. Even though alpha is really short, if you're trying to take the cup product in itself, it gets really big really quickly. In only 2 minutes, it's already 3 gigabytes of RAM, even though alpha is just 8 lines when normalized. And the reason is that the cup product is not that easy to define. So basically, just all the higher paths that you have in the definition of alpha are gonna blow up together when trying to compute it. So we're hoping to get a better definition someday. So to sum up, basically, we've given a really practical definition of the cohomology ring and of the multivariate polynomials. And mostly we have emphasized how important is the data structure when trying to formalize. And we have also explained doing so a fun application of the structural identity principle, because after all, you may not want to give up on definition using sequences. We have also explained a bit about how to characterize them and how to use computation. And we have also shown the limitation of computations. But what is nice is that we can actually already do some stuff with it and actually win time. So you will find a bit more stuff in the paper, much more details, of course, and some computation. And also what I haven't said is that what we have done so far is Z cohomology, but we have also formalized some Z mod 2 cohomology ring and defined more generally with Axel's work G cohomology. And so you will find some details on that in the paper. So thank you very much.
Thank you. So we have a couple of minutes, so if you have any questions, then please ask.
Thanks for the talk. Just so I got the idea correct, on the, I think it's the previous slide, or maybe the one before. So just to make sure I understand, was the idea here that if you try to compute the goal alpha equals phi 1 of 1, you would like that should compute to just reflexivity, but it takes too long to compute? Is that the idea?
You mean this one?
So this one, so the way I understand it is you prove this by saying we can apply the inverse rules to both sides of the one above. But this should compute, like I'm saying, is it true that this would compute through given enough resources? Or
Not really, because
okay.
you have to think that canonicity is really nice, but we're working with cohomology groups. So basically, there's no reason why you couldn't have a computation like a computation by local or something like this, especially that Cubical like that does not compute. So what we would do is that basically we're in H2, and we have that H2 of K2 is just equivalent to Z mod 2. So basically, we would bring alpha and phi 1. Oh, sorry. Yeah, I'm sorry. You would just like no, actually, you would have to bring them back. You're in H1, sorry. You just bring them back into Z. This way you're in Z. In which case you have canonicity, so then you can actually compute them and compare them. And here, this would just simplify, so you may not as well compute it back and forth.
Okay.
So that's the idea. But it's true that basically, here you would like to compute that. And here you're in H2, so you would like bring it back in Z mod 2, try to compute it. But the thing is that you can't even normalize phi 1 of 1. So you have no hope of normalizing it, taking the cup product, then bring it back to Z mod 2 directly.
When you say you can't normalize it,
That's almost time for the next speaker. Maybe if it's short, you can, it's okay, but okay. Then let's thank the speaker again.